What if you could launch a multi-billion-dollar satellite twice? The first time, in a digital world, where every failure is a lesson, not a catastrophe. This isn't science fiction. This is the revolutionary power of the digital twin, and it's changing how we explore the final frontier. So, what exactly is a digital twin? It's a living, breathing, virtual replica of a physical spacecraft, updated in real time with data from its real-world counterpart. It's not just a 3D model. It's a high-fidelity simulation environment that understands physics, material science, and operational constraints. Before a single bolt is fastened, the digital twin undergoes grueling verification. Traditionally, this meant expensive and limited physical tests. We'd test for launch vibrations, extreme temperatures, and vacuum exposure, but we could never perfectly replicate the harshness of space. With a digital twin, we can simulate scenarios impossible to test on Earth. Imagine simulating a 5-year journey past Jupiter. We can model solar radiation effects on electronics, micrometeoroid impacts, and material degradation over decades, all before launch. This allows engineers to identify and fix design flaws at the earliest, cheapest stage, the digital drawing board. The result? A massive reduction in costly physical prototypes and a radically accelerated development timeline. By integrating data from manufacturing, we can even account for tiny real-world imperfections in the final build. The twin becomes a perfect as-built record, not just an as-designed ideal, making its simulations incredibly accurate. But the digital twin's mission doesn't end at launch. In fact, it's just beginning. Once in orbit, it becomes an indispensable tool for operations. Ground control faces immense challenges: communication delays, limited sensor data, and the inability to physically inspect the spacecraft. The digital twin acts as a live virtual mirror of the orbiting satellite, receiving the same telemetry data in real time. If an unexpected reading comes in, operators can see the problem in a rich 3D context instead of just numbers on a screen. This is where its predictive power shines. The twin can run simulations faster than real-time to forecast the future state of the spacecraft. It can predict component fatigue or thermal stress days or weeks in advance, enabling proactive, not reactive maintenance. Mission controllers can use the twin as a safe sandbox to test solutions for anomalies or upload new software patches. They can play out what-if scenarios. What if we reorient for a better signal? The twin simulates the power drain and thermal impact before a command is ever sent. This dramatically reduces the risk of human error, which can be catastrophic when your asset is millions of miles away. This continuous feedback loop of real-world data refining the virtual model makes the twin smarter and more accurate over the spacecraft's entire lifespan. The future is even more exciting. By integrating artificial intelligence, digital twins can start to learn and operate autonomously. An AI-powered twin could self-diagnose complex problems and suggest solutions that a human operator might miss. Imagine managing an entire constellation of hundreds of satellites. A fleet of interconnected digital twins could optimize the whole network. They could coordinate to avoid space debris, manage data traffic, and ensure seamless global coverage without constant human oversight. The applications extend beyond Earth's orbit to deep space probes, Martian rovers, and even future lunar bases. Each digital twin would be a virtual research and operations outpost, allowing us to explore farther and more safely than ever before. From initial design verification to real-time operational command, digital twins are fundamentally de-risking space exploration. They are making the impossible possible, ensuring that for every mission, the first launch is as close to perfect as the second, virtual one.